All right, in this video, we're going to look at 3 more examples, some concept tests here. Hopefully these will be pretty straightforward given what we've been talking about recently. So in the first one up here at the top, we're supposed to rank those lamps, those light bulbs, from brightest to dimmest. All right, now the first thing to think about is, well, as the current comes out of the battery, all of the current is going to go through light bulb 1, and then it's going to split and go through C, D, and B. Now, all of the current must go through A. If all of the current is going through A, it has the largest current. If it has the largest current, then that means it's going to be the brightest. Okay, so A will be the brightest. Now we look at the current. The current is going to split and go through B, C, and D. Now there is going to be more resistance in the CD path. There's more resistance here than there is here, right? Because when you have 2 resistors in series, those 2 guys, the C and D, are going to add up to be more resistance. Now what that means is that we should get more current going through B. Now, if we have more current going through B than we do through C and D, more current means it's going to be brighter. So B should be the next, and then C and D will follow after that. Now, C and D are in series, and so we expect to get the same potential difference across each of those because they are identical. It doesn't matter that one comes before the other. That's the way that it works. So there we go. We've got A as the brightest, B is next, followed by C and D, which are equal. All right. Now, concept test number 2. Bulbs A, B, and C are identical. Closing the switch in the figure causes which of the following changes in potential difference? More than one answer may be correct. All right. So before we even look at the answer, you can look at the answers if you want, but let's go ahead and see if we can figure out what happens here. So before the switch is closed, your current's going to come out of your battery. It's going to go through A, B, and C, and then back to the beginning. So whatever your potential difference was there, right? Now it's labeled as E. That's our EMF. Remember, the electromotive force, which is just the same thing as the potential difference. So whatever your EMF is there, right? Your A, across A, you're going to get 1/3 of the potential difference. Across B, you're going to get 1/3 of the potential difference. And then across C, you're going to get 1/3 of the potential difference. So therefore, each one will be identical. Now, what happens then when we close that circuit? Well, when we close that circuit, then the current is no longer going to go through everything, right? The current is now going to go through A, and then B, and then instead of going through C, it's going to go through this resistanceless wire and then back to the beginning. So C is going to completely change because there's not going to be any potential there anymore. All right, that potential is all going to be the same. Nothing's flowing through C anymore. And then what we can do is we can say, well, now the potential that I had needs to split up evenly across A and B. So A is now going to be V over 2, and B is also going to be V over 2. So now, and across C, of course, will be 0. So now we're ready to go and see if we can figure out what the correct answer is. So letter A, the potential differences across A and B are unchanged. Nope, that doesn't really make sense, right? We know that A changed. It has a different potential there. So definitely not letter A. On to letter B. The potential difference across C drops by 50%. Now, C went from V over 3 to 0. It dropped by 100%, so not B. Letter C. The potential difference across A and B increases by 50%. Okay, well, what's 50% of 1/3? Well, 50% of 1/3 is 1/6. And if I add 1/6 to that, I do actually get V over 2. Now, if that math is challenging for you, then go ahead, work it out, show the fractions, and you should be able to figure out. Now, one way to do it, I guess, would be to say, well, the potential difference across C, which was V over 3, that's going to split up. Half of it's going to go to A, half of it's going to go to B, so it does increase by 50%. Letter D, the potential difference across C drops to 0. Yes, that's what we just talked about, because no current will be going through it. And if no current goes through it, the potential difference will be 0. All right, lovely. We got one more question we're going to work through here. What is the current in the 5th wire? So you'll notice that I have 5 wires here. So I've got 2A, which is coming out. I've got 3A, which is going in. I've got 6A, which is coming out. And I've got 4A, which is coming in. So the question is, what's going to happen here? Now, the easiest way to do this is to use Kirchoff's first law, which is that the sum of the currents in and out should equal 0. So I'm just going to start with that question mark there. So that's going to be my unknown current. Okay, then I'm going to go clockwise here. So the 2A is going out. So I'm going to count the out as being minus. So it's going to go out 2 amps. Then I come up to the next one. That is coming in 3 amps. Okay, then I've got a going out 6 amps. And then the last one is I've got a going in 4 amps. So anything going in is positive, anything going out is negative. The total needs to be 0 so that the going in and the going out are equal. Now, are there other ways to do this? Yes, absolutely there's other ways to do it, but I wanted to show you a way using Kirchoff's law. So at this point, you should be able to put those together. -2 plus 3 is +1. -6 would be -5. Plus 4 would be -1. And so I end up getting I minus 1 equals 0. So the current is 1 ampere. Now that is positive. That means that it's coming in. All right. And therefore, we know the current, we know the direction, and you'll notice now that I now have 3 coming in, 4 coming in, plus 1 more, so that's a total of 8 going in, and I have a total of 2 plus 6, that's 8 going out, and therefore it matches our conservation of charge and Kirchoff's first law, which is that the sum of the currents going into a junction must be 0. All right. There we go. That's the end of those examples.